All right, so this is the notes on a different way of solving a linear system algebraically called elimination. Last day was substitution. It's actually the last formal notes in this entire unit. There is one more section of Chapter 8 that's a very important section, but it's about just example problems of systems and solving them algebraically. So it's not so much a section where you need notes for, you just need some examples, and I will work through a few examples, but it's a little different. Essentially just problems I'm going to work through, but there's no new concepts. That's it. So the last new concept of this entire unit is what it means to solve a linear system using elimination. So again, here we have a system. Here we have the two variables a and b, and I want to eventually solve for both a and b. Now notice in this system, if we try to use substitution, it'd be pretty painful because no matter what, no matter which of these variables we try to solve for, try to isolate, you're going to end up getting some fractions from the very start, and then you have to substitute that back into the other equation, and things will get messy pretty fast. So this is a good example of where substitution is not wrong, but it's needlessly difficult, not if we understand elimination. And so the idea for elimination is I want to combine these equations together. And again, right now, what do I mean by combining two equations together? It's actually pretty easy to combine equations together if everything's lined up. If all your like terms are lined up like they are here, I could literally just put, say, 6a plus 4a and make a new equation that starts with 10a. And I can put together 5b plus 3b and say that's positive 8b. And 24 plus 12 is 36. And so by just literally adding these two equations together, I've come up with a third equation that relates to the ones above. It doesn't do me any good, but I can do that. And I can, I can combine equations any way I want. I can subtract equations, plus we already know that we can multiply and divide both sides of an equation by any number. So this idea that we can combine equations together to create new equations that are related to the ones above is probably a new idea. And right now, from what I just did, it's not wrong, but what I just did is not helpful. I now have a third equation. Well, that just makes it look even more confusing. So how can this be useful, this idea of combining equations together? Well, it's useful if we first find a way to make it so that two of my terms, my like terms, are opposites of one another. So for example, let's focus on my b's. One's 5b, one's 3b. I can just see, if I look ahead a little bit, if I take this equation and multiply by negative 3, and I take this equation and multiply by positive 5, it doesn't take much for me to look ahead, because just knowing my 5 times tables, that those two b terms will become opposites to one another. In the first equation, that'll become negative 15b. This will become positive 15b. And the point of that is when I combine these equations together, those will eliminate one another. They will cancel each other out, and there'll be no b term left. So let's just do it. So I got to make sure I multiply everything in the top equation by negative 3. Otherwise, the equation's no longer equivalent. So for the top equation times everything by negative 3, I get negative 18a minus 15b equals negative 72. Right, multiply both sides. And for the bottom equation, I chose to multiply everything by 5. It's not the only way of doing it, but this will work. And so multiply everything by 5 here, I get 20a plus 15b equals 60. And now notice, if I now combine these equations together, right here together, keeping all my like terms lined up to make things convenient, that cancels out completely. We say those terms have been, I've eliminated them. So all that's left is negative 18a plus 20a. Negative 18 plus 20 is 2, so 2a equals, and negative 72 plus 60 is negative 12. Suddenly, I have a really simple equation. 2a equals negative 12, which means if I divide both sides by 2, a must equal negative 6. And I now know a. I know one of my two values. Before I go on, keep in mind, I could have also, if I went back here, I could have multiplied the top equation by positive 3 and the bottom equation by negative 5. My next step would have looked a little bit different, but my b's would have still canceled out, and eventually I would get the same answer. Or alternatively, I could have found a way to cancel out a. Maybe multiply the top equation by 2 and the bottom equation by negative 3 to make them both 12 or negative 12. Either way, I'll go back to what I had, just so this doesn't get extra messy. And now that I found a, how do I find b? Well, similar to substitution, but this time it'll take a bit more work. Now that I know a is negative 6, I can put that negative 6 into any equation I see. This one, or these ones over here. I'd rather not use the later ones because they have larger coefficients. I'm kind of lazy and want to deal with smaller coefficients. So I can put this a equals negative 6 into any equation that has an a and a b. So I'm going to put it into this equation right here. So I'm going to go to that second equation, although I don't have to. I'm going to substitute that a with negative 6. And so now I have 4 times negative 6 plus 3b equals 12. So now I can solve for b. And this time it should just take me a few steps. 4 times negative 6 is negative 24. Add 24 to both sides. I get 3b equals 36. Divide both sides by 3. And I got my value for b, which is 12. There you go. So I'm done. Right? A equals negative 6, b equals 12. So in this case, this is a perfect example where elimination is quite useful, and it's because substitution would be quite awful here. If you just, I encourage you to try it if you're not sure. Just pick one of the variables and try solving for it, and you'll right away create some fractions or decimals, and then you got to put those right back into the other equation, and just, you'll get the same answers theoretically, but it would be more difficult, right? And so this is a perfect example where elimination is quite useful when you have equations like this. All right, so I don't need to have lots of examples here. This is sort of a special case, though. So let's look at this one. I want to solve using elimination, although I don't have to. So what I want to do here first is I want to pick a variable to cancel out. I don't know, look at x this time. I can just see if I multiply by top equation by negative 3, I can see my x's are going to cancel out. However, my y's are also going to cancel out. So let's do it. I'm not even going to change my bottom equation. My top equation will now become negative 9x take away 6y equals negative 21. I multiplied all the terms by negative 3. My bottom equation I'm going to leave alone. Put these together. Negative 9x plus 9x is 0. Negative 6y plus 6y is also 0. So all I have is 0 on the left-hand side. I need to write that down. I can't just leave it blank. On the right-hand side, negative 21 plus 16 is negative 5. And I end up with this strange statement. I'm saying that 0 is equal to negative 5. No, it's not. Okay, 0 is not the same as negative 5. So what does this mean? This means one of two things. It could have mean I made a mistake. I didn't. I didn't do much work here. Double-checked my steps. I've multiplied everything properly. So it could mean I've made a mistake. I haven't. If I haven't made a mistake, what does this mean? This means this system has no solutions. Anytime you end up with something like this, where you get again, 0 equals a number that's not 0, which is not true, that means there's no solution. So this here means there is no solution to this system, which we saw at the end of chapter 7. And remember, what does it look like when a system has no solutions? The lines are parallel. Right, so without even visualizing these, I now know this is a system of two parallel lines that'll never cross. And I got to that conclusion really quickly. Notice I didn't actually have to graph anything. And so here's the last question, another sort of special case. Okay, so I want to find a way using elimination from how it's set up to cancel out a variable. I can see if I multiply my top equation by negative 7, my x's will cancel out, and so will my y's. Okay, so let's see what happens this time. So if I multiply everything by negative 7 in my numerator, I get negative 35x plus 21y equals positive 42. My denominator, if I just leave it alone, I get positive 35x minus 21y equals negative 42. I did nothing. Combine these together. Well, these completely cancel out. These completely cancel out. And my constants cancel out. So what do I have here? I can't just leave it blank like this. What I have here is 0 on the left-hand side equals 0 on the right-hand side. Well, unlike before, this is true. My last question, I had 0 equals negative 5. That's not true. 0 is not the same number as negative 5. But 0 is the same number as 0, so great. So what does this tell me? This tells me, well, either that I made a mistake, like before. If you ever see something like this, always double check your arithmetic. But everything's correct. So this means, as you can maybe guess, that there are an infinite number of solutions, which means the two lines are on top of each other. So it means there are infinitely many solutions. Or coincident lines, they like to call them in the textbook sometimes. Really, your two lines are the same. If you graph them out, they're exactly on top of each other. And so every single thing we learned about in chapter 7 in terms of linear systems visually and how many solutions there are and how to solve them, we can now do all of that algebraically. It's not inherently better, but sometimes it is. Sometimes graphing is really quite pleasant to do. I mean, Desmos is pretty easy to use, but we don't need that anymore. And so, like I said, the last lesson in this section, in this unit, 8.3 in the textbook, is really nothing new in terms of concepts. It's just a variety of problems for you to try solving. And so the last video will just be a few group problems that I'll solve, but they're not so much formal notes. And